So I started my sustainability journey about, oh my gosh, mid 2000s. And I did it because I read an article about my home country, Colombia. I was born in Colombia, and I learned that Colombia would not be a coffee producing country by the year 2050 if climate change remained unabated. And that really shocked me, right? Because at that time we talked about climate change as sea level rise, and nobody actually said that climate change was a fundamental change to our ecosystem, to our way of life. I couldn't imagine that in 2050, during, I hope, my lifetime, we would not be drinking coffee from Colombia. And so that really made me appreciate the urgency of the problem, that it wasn't a future problem, and that it was much more than sea level rise. Now, that was 2005. And the IPCC has been talking for decades and decades about bending the carbon curve. And as you can see, we haven't even flattened it, much less bent it. And what stuns me about this curve is the fact that even during COVID, when we literally shut down our economy, we didn't flatten it that year. We didn't have a reduction that year. We continued to put carbon into our atmosphere. Now, it's very trivial to say we're going to bend the carbon curve, but it's actually quite difficult. So, my lovely girl greyhound, everything in our daily lives comes from carbon, and it's all made in petroleum refineries. From her food to her collar to her toys to her bed, all of that is fossil carbon derived. And so we think about carbon, it's in our materials, it's in our clothes, it's in our planes, it's in our food, it is in nature, it is in us. And so saying that we are going to reduce our carbon emissions is actually not trivial. So to me, the problem isn't the carbon, but rather where our carbon comes from. And at LanzaTech, we believe that there's enough carbon above ground to make everything we need. And that what we need to do is transition to an economy where we stop using petroleum and natural gas and instead use the carbon that's locked up in municipal solid waste, waste biomass, industrial emissions, CO2 in our atmosphere. To us, this is the feedstock, this is the resource. And I can show you today that this is not science fiction, that all of these products we're showing you here, we've made from recycled carbon emissions, and that it is not science fiction. This is our first commercial plant in China, and it's at an industrial site, it's at a steel mill, and it takes emissions that would go out the flue of the steel mill and converts them to ethanol. We literally take the carbon emissions and put them in those bioreactors and ferment them. And it's commercially operating, so it works. You can cross the valley of death. That's the message. Thank you. So how does the technology work? Okay. It's literally a gas fermentation. Instead of fermenting sugars, we have an organism. It's a bacteria. It's a naturally occurring bacteria. And it picks up CO, CO2, and hydrogen. And what we've done is we've developed a continuous bioreactor. It looks like a refinery unit operation. Sugar is soluble in water. Yeast can go grab it and ferment it. These gases are not soluble in water. So really, it's as important to have an organism that works as it is to have gas get to the organism. So we've developed a bioreactor that's extremely efficient. We recycle 90% of the water. We recycle the media. It's optimized. And where do you get these gases? Industrial sites like steel mills have 40 to 60% carbon monoxide emissions that get then emitted and flared as CO2. So what we're doing is we're preventing them from being emitted, we're capturing them and converting them to product. So it's a mitigation strategy. What I think it's particularly important is that combustion of carbon, as you well know, is not a greenhouse gas exercise. It's also a particulate emissions exercise. And so what you're doing is you're preventing pollution as well as preventing greenhouse gas emissions. You can also take agricultural waste, gasify it, make CO and hydrogen, convert that to ethanol, and you can use CO2. The catch with CO2 is you need hydrogen. Carbon monoxide has carbon and energy for the organism. It's almost like sugar. CO2 doesn't have any energy, so as long as you bring in hydrogen, you can convert CO2. We've developed technology to make sustainable aviation fuel. We've partnered with people that can take the ethanol and convert it to polyester and other materials. Don't need to reinvent that. People already know how to take ethylene to materials, and all we have to do is take ethanol to ethylene and make materials. The other thing I didn't mention, and I should, our only co-product is biomass. So in that bioreactor, the bacteria is alive and dividing. And so you don't want to plug that reactor, right? So you're constantly taking bacteria out. We dry it and we sell it as animal food. We have all of our plants in China selling it as actually fish food. It's 90% protein. That's our only co-product. And 10% of the carbon that comes into that reactor becomes biomass. The rest becomes ethanol. Obviously, if you put it in jet fuel, you've got to recycle it. If you put it in materials, right, no matter what you make, you're going to have to take that someday back to the store and turn it back into another dress. So that's what we focus on. I showed you the picture of the first plant, the one that we started in 2018 in China. These 4 are in China using steel and ferroalloy emissions. We have Roundtable for Sustainable Biomaterials and ISCC certification on 2 of the plants. We work with many brands, and so that's what they would like to see, is certification and validation of the life cycle emissions. We're starting up 2 plants, one in Europe with ArcelorMittal in Ghent, and the other one in India with Indian Oil at their Panipat refinery. This one uses refinery off gas. That gas is a mixture of hydrogen, CO, CO2. 50% of the carbon in the ethanol comes from the CO2. It's not gigatons, but it's a journey to gigatons. Today, at the full capacity, which 2 plants are not at, we would be abating 500 tons of CO2 per year from entering the atmosphere and making 300,000 tons of ethanol. And let me just give you a close-up of the plant. This is our Ghent plant. So you can see the orange pipe brings in the gas. It goes into the 4 bioreactors. It goes into the bioreactors where it's fermented. If you look at that picture, what it should give you a sense of is that what we're actually doing is building refineries, right? And that's the scale and the magnitude of building out a process industry. You know, I don't think of ethanol as an end product, right? Hopefully the world is going to electrified cars and so really, but for me, ethanol is a feedstock, ethanol is an intermediate, ethanol is something we can make into pretty much every product we use every day. And that's how we think about it. And so that's why we've developed technology to make sustainable aviation fuel, and also why we've developed technology with partners to make materials. So for us, it's about reducing carbon emissions, and it's about the circular economy. It's about converting into products. How many products have we made or do we make? These are all commercial products. Fleeces with crag hoppers, Adidas running shoes, Coty perfume. These are all products that either are still on sale or have sold. And again, not science. An H&M pair of pants. The polyester was made from steel mill waste gases in China. And that's pretty cool. So that's really the point. That's what we're trying to do. And right now, what we do is make ethanol, and we take that ethanol and convert it to products through ethylene. Ethylene is the largest petrochemical intermediate used today. It it's a $200 billion market, and it accounts for 500 million tons of CO2 emissions every year. And the reason I want to say that, and I want to emphasize that, is because we've devoted ourselves to trying to abate certain sectors, power, fuels. But we got to remember that all our materials are also, that production is carbon emitting. So working on reducing emissions of production of materials is also quite important. We just got a grant from the Department of Energy to integrate into a naphtha cracker. Cracker is how most of the ethylene in the world is made today. And what we're going to do is, instead of bringing in more petroleum, what we're going to do is make more ethylene from the CO2 that comes from that cracker. So same amount of feedstock, CO2 that would be emitted, converted to ethanol, and at the same location, converted to ethylene, and then integrated with the whole ethylene production, increasing the amount of ethylene, more product, same amount of feedstock. So that's the point, and that's our next generation, so we don't have to move the ethanol from one location to another. I want to say a few words about sustainable aviation fuel. Aviation fuel is 2% of global emissions. What we've done is we've said, look, nobody at the time that we started doing this was taking ethanol to sustainable aviation fuel. The fact is that ethanol can be made from anything. And if you believe in a distributed production world where local resources, local waste resources can be converted to ethanol, ethanol is a brilliant intermediate then to make things like sustainable aviation fuel, because now you're using a country's own resources. So what we've done is we've launched a company called LanzaTech, which can take ethanol to 90% sustainable aviation fuel, 10% diesel. And so we're really excited about this. We have lots of great investors, but we're excited about the integration of waste resources to fuel. We've tested in flight. We have tested it on delivery planes, and this is the world's first 10 million gallon a year ethanol to sustainable aviation fuel plant. It is in Georgia. It's in a rural community. It's actually in Soperton, Georgia, one of the poorest counties in Georgia. And it's really cool to have that type of a production facility there, creating jobs and making product. This plant is starting up in the next 4 to 6 weeks. So we're really excited about that as well. And it's all about putting a lot of steel in the ground, but it's about creating jobs and creating economies. It's kind of interesting when you take a step back. There's actually a book that was written by Bill McDonough. It's called Cradle to Cradle, and to me it's like the manifesto for anybody who's interested in the circular economy. And one of the examples that he cites is, sorry, I wanted you to get the caption so that you know the name of the book, is the cherry tree. And so he uses the cherry tree as kind of a nature example, right? Nature doesn't waste anything. We waste things, but not nature, right? If you have buds on a tree, they fall, and they're either fertilizer or they're the next tree. Nothing is wasted. So on the other hand, there's us. We do waste things, right? And so to me, that's actually one of the interesting aspects of what we do and what many of you are doing, which is this is a carbon opportunity, right? Look at how much carbon is locked into municipal solid waste. And so our goal is to unlock that carbon. And to do that, we just use the same technology, but pop a gasifier in front. And so really this whole ability to take a dress that's been made or a pair of running pants and then turn it back into a dress is pretty exciting. Now, the way to do this, I'm a thermocatalytic chemist. I don't know biology, but I believe biology is actually an important part of doing this. And the reason why biology is going to be important is because, well, first of all, biology, organisms like us want to survive. If you want to use waste, you're using a very dirty resource, right? And so if you want to use a dirty resource, you need to use something that isn't going to roll over and play dead the minute it sees a contaminant. And biology doesn't do that. It's very robust. Again, organisms evolved to survive. The other thing that organisms can do, which thermocatalysts cannot do, is just what you would do if you were driving on this road. You're visually interpolating across what you're seeing so that you can drive safely. Well, that's what organisms do. And so what I'm showing you here is something that a thermocatalyst could never do. This is a municipal solid waste plant that we have in Japan. We take municipal solid waste and convert it to ethanol, not at commercial scale. So this is done at a demonstration scale. And you can see the inconsistent carbon-hydrogen ratio. If you gasify plastic, if you gasify food, you get a very different carbon-hydrogen ratio. So you see that variability, but look at the consistency of the ethanol output. The only thing you change is your yield, but you're still making the same product. And this is the power of biology. This is our commercial plant in China. Even a steel mill gas is not consistent, and yet we always make ethanol. So for me, biology is actually central, right, to the circular economy. And it's the original circular economy. The last comment I would make around that is what we've done, and I know this is meant to be a story of scale, and it's really that I keep talking about biology, but we're not a biology company. We have as many chemists and engineers in our company as we have biologists. And so to me, one of the things that's important is bringing all the different approaches together so that you can actually do something disruptive and you can get something to scale because you're actually bringing other disciplines into the mix. And then the other thing I have to do, I'm in California, I have to do the obligatory AI, right? So forgive me. Obviously, if you want to do something with biology, genetic engineering, which is critical to improving biology and understanding genomes, AI is an important element of that. And we've been doing AI for 10 years. We have so much data because we collect all of our data in the lab, in the pilot, in the demo, in the commercial scale. But I want to talk a little bit about synthetic biology. And the way I think of an organism, all an organism is a chip. It's an electronic device. But instead of worrying about moving electrons around, you're moving carbon around. You're moving carbon through the bacteria in a way that it makes whatever product you want it to make. And so basically, a bacteria is just an assembly line. And what you end up having to do is understand the genome of the bacteria and then figure out the most effective way to channel the carbon to make the product you want. And that's what we do, right? We understand our bacteria at the genome level, but there's no way a human being can predict the pathways to use. This is where computing power matters. And it is computing power that enables genetic modification, because at the end of the day, this is something we couldn't do 10 years ago, right? These massive data sets, this massive need to understand pathways was not possible before. This is why I believe this is also the century of biology. And then what you do is you figure out the pathway and then you put it in a biofoundry and you use robots and you make new microbes that make other stuff. And I'll give you one example. I emphasize polyester. How is polyester made? By us, at least. Well, by everybody. You go ethylene oxide, MEG, polyester. And of course, if you work with us, you have to start even earlier. You take a product, you gasify it, or you use a gas, you make ethanol, then you make ethylene. And that's how we make bottles, and that's how we make clothing. And what I want to do, and what we've already proved we can do, but not at commercial scale, is just go from the gas to the MEG. Now you're skipping steps. And by shortening and essentially putting the supply chain in the organism, you can have an economically viable route. And what is also cool about biology is that once you build a bioreactor, like all those massive refineries I showed you, to make ethanol, and you have a microbe that makes something else, you do not need to build another plant. You would put the same organism in that plant to make a different product, right? This is actually going to change how commodity chemicals are made. So talking about a new carbon economy. And so back to the beginning, we have to reduce carbon emissions, we have to power the circular economy, and you're all here because we have to repair our food system. And fundamentally, what I've shown you, co-product is biomass, but I can also tell you we are making biomass as a primary product. And that is the next stage of our journey as LanzaTech. We've spent 18 years developing that bioreactor. Making food with it makes sense. And so I'm going to go back to why we're doing this. And I'll quote Tom Chi because I heard him make this comment once. We spend all of our time looking at IPCC reports, worrying about whether we're going to get to 3 or 2 or 4 or 5, and we debate what that means. The fact is that the catastrophes that we see unfolding, we're at 1.3. So frankly, I don't want to debate 2, and I don't want to debate 3 or 4. What I want is for us to reinvent ourselves. We have to reinvent, and the only way, I believe, that you ever change anything is through technology. It's innovation, it's disruptive innovation, which is what you're all doing. And this is what happened with solar. Solar isn't just about power. Solar is about creating new economies. And I believe in a future where biology enables distributed production from local waste resources. I believe that's what's going to create a circular economy, and that is what we need to change our carbon trajectory. And to quote one of my favorite chemists, you never change anything. You can't nibble around the edges. We're way past nibbling around the edges. We need to step off. We need to literally jump off the path we're on and create a new carbon economy. And I hope that what I've convinced you is that that's possible. I've convinced you to rethink carbon, to rethink refining. Refining isn't about petroleum. Refining is about converting CO2. That biology will have a role to play, and that with biology and CO2, we can make everything we need from every waste resource, including CO2, so that everything we have can be made in a different way. And I beg you to start looking at your bottles, start looking at your clothes. Where is my carbon coming from? Where is it coming from? I know these are long days and long nights, and it's very hard. But impossible, every time you hear the word impossible, take it as a dare. Challenge yourself to change everything, because we can. And I've always loved this quote because I love the end. Impossible is potential. Impossible is temporary. Impossible is nothing. Impossible is nothing. And the only way impossible becomes nothing is if superheroes that you all are come to the table and choose to change everything. And so on that note, I thank you for giving me the opportunity to be here.